Okay, let me start with the lecture number 3. And in particularly, I would like to discuss about an example how to make use of the so-called Fourier series that we have already developed in the previous lecture number 1 and lecture number 2, and how does it apply for this particular example. Now, if you take a look in figure 11.1, we can see the horizontal axis here represent time, and the vertical axis here represent the periodic function f of t, which is given. Now, this periodic function f of t is defined according to this formula, which basically say if the time t between 0 and pi, then the function f of t is equal to t. On the other hand, if the function time is given between the range from pi to 2 pi, then the value of f of t is defined as equal to the constant pi. So this function can be plotted according to figure 11.1. As you can see, if time is between 0 and pi, then the function, the periodic function, is defined as f of t right here. And if the time is between pi and 2 pi, then the periodic function f of t is defined as a constant equal to pi. Okay? So you can see this period from capital T is a period going from 0 to 2 pi in this particular example. And as a matter of fact, you can see after the period 2 pi, the function repeated itself, as you can see from the dotted figure in here. So the problem becomes, given a periodic function f of t defined between 0 to 2 pi, how do we represent this periodic function using Fourier series? All right, so let's see. According to the formula that we learned earlier, in order to use a Fourier series to represent a periodic function, we have to calculate the coefficient a0 according to this formula, which is 1 over t times the integral from 0 to the period t. In this case, the period t is equal to 2 pi. And you have to integrate that with the function f of t is given. Well, in this particular example, the period t, you can replace it by 2 pi. However, the integral from 0 to 2 pi, you have to split it into two parts. The first part going from 0 to pi. And the second part is going from pi to 2 pi. Now, for the first integral between 0 to pi, the function is defined as t. And for the second integral between pi and 2 pi, the function is defined as equal to pi. So we can easily integrate these two integrals and evaluate it between the lower and the upper limit. Then we can come up with the numerical value for the constant a0 is equal to 2.35619, which is the same thing as 3 pi divided by 4. So we already finished the evaluation of the constant a0 for the Fourier series. The next thing is we need to calculate the constant b sub k of the Fourier series. From the previous lecture, we know the formula we already derived to calculate the constant bk is given by 2 over period t, the integral of the given periodic function f of t times sine of k omega naught t. Don't forget, omega naught represents the angular frequency, which is equal to 2 pi divided by the period t. And in this example, we know t is equal to 2 pi. Therefore, omega naught is equal to 1. Okay? So basically, we have to figure out this integral and realizing that omega naught is equal to 1. And furthermore, the index constant k here, it can go from 1, 2, 3, all the way to infinity in theory. So let us try to continue to figure out the constant bk. All right? So, as before, we would like to split the integral into two integrals. The first integral going from 0 to pi. And for this integral, the periodic function is defined as t. The second integral, the limit will go from pi to 2 pi. 2 pi. And for this integral limit, the function f of t is given as pi. So now we should be ready to calculate the constants bk corresponding to different value of k. So for example, if you let the index k right here is equal to 1, we let the index k here equal to 1, then we should be able to calculate b sub 1. And that is given right here after we finish the integration. Similarly, we can let the index k here is equal to 2. The index k here again is equal to 2. Then we can calculate the constant